have to implement. So what does that have to do with a Lisp interpreter? Well, a Lisp interpreter is essentially a text representation of an input S expression. And its job is to convert the text into an input S expression and then evaluate the input S expression to create an output S expression, and then convert the output S expression into some output text and give you back the output. That's its job. Okay? So this is how we are relating it to what you do with Lisp. Okay, as far as you're concerned, you type in some text, you get back some text, that's the interpreter. But internally what's happening is that there is some parsing, and this parsing is given to you by Andrew, that converts the text string into an input S expression. If it's not a legal input S expression, Andrew's interpreter throws an exception. You've got to terminate the program and start it again. In Common Lisp, you go to abort that particular, it's a little nicer. But that's basically what a Lisp interpreter is doing. Okay, so Lisp interpreter reads, does some stuff, etc., then does an eval, and then prints. So this READ-EVAL-PRINT-LOOP is something that got invented in the context of Lisp, and it defines an interpreted language, okay, like Lisp. Okay. So in the output, you should be able to get any S expression, right? Because otherwise you're not using the full power of S expressions. And I'm going to argue that in the input, based on what you've seen, the input S expression has some limitations. And so what do you feel are the limitations? Or could be, what can you imagine, or what do you know, what can you derive? The input must include some operations. You're getting there, right? So plus 1, 2 is an input, and plus is an operation. Good. Somebody want to extend his definition? We haven't quite defined operation, but your intuition is right. Right? What else can you type? Can you type something that's doesn't have an operation and get back a result? It may be useless. What can you type? I see a nod here. Without an operation. I can enter plus 1, 2. What about just entering 1? As it turns out, you can. Okay, it may not seem very useful, but you can. Okay, so the input S expression can be an atom. Okay, and we've seen it must be you said it must have an operation. You can type plus 1, 2. Can you type just within parentheses plus? It'll give you an error, right? So it's a function application. A function application, we haven't quite seen what that is, but can you think of a data type that represents a function application? So we have atoms, we have composite X expressions. We know it can be an atom. And a function application would be not an atom. Okay? So if it's not an atom, is it one of the other two types? Is it a list or is it a tuple or both? From what you've seen of Lisp? So what does the function application have? It has an operation name plus what does it have? Arguments. So the function name and arguments together would form a what kind of data type? A list, not a subtle question. Okay, so at the outer level it can be a list, right? It can't be just a composite S expression. It has to be a list because we're talking of a list of items here. And then I can say plus, and then plus 1, 2, and then again plus 1, 2 with a nested. So I can have nested applications also. So I can have within the list sublists, which are all function applications, or I can have atoms somewhere there. So basically, I'm not allowed. So can you now say what is? Can you now define some restriction on input S expressions? So we have a tree. It can be an atom or it can be a tree. And what's the qualification of the tree? Lists or nested lists. So no tuples inside. Okay, because it's all either function applications or it is atoms. Okay. So basically, an input S expression does not contain tuples. Okay, so it can be an atom or it can be a list, and the list can have nested sublists in it, but we don't have nodes that are not lists or atoms. Okay, composite expressions that are not lists. But you can compute. I mean, we are talking of tuples, so you can compute them. So these function applications can create S expressions that happen to be tuples. So now you see why it's called a list processing language, because the input is all lists. Okay? And then, of course, what you can create are tuples also. You can create lists, or you can create tuples, or you can create atoms. Okay? So the output, you can give it a list as expression, and it can compute an atom. Okay? Or it can, of course, compute a tuple or another list. Okay, that makes some sense. Okay? When we go and evaluate lists, which right now, so all the examples you've given, have all had this feature. Okay, that you had to evaluate all these sublists, and the evaluation happens to have operations. Okay, so there's a notion of evaluating to compute an arbitrary S expression. So that's interesting. The Lisp interpreter doesn't go and decide how to evaluate. The Lisp interpreter creates an input S expression and then asks the input expression to evaluate itself. Very object oriented. The object decides. Okay, so the semantics of what evaluate does is with the S expression, input S expression. Okay, so there are three steps here that we have to worry about. We know we are going from S expressions to S expressions. We know we are entering text. We know we are getting text. Okay, so we can defer the evaluate to later and just try to figure out how do we go from what's the mapping between text and S expressions. Okay, what is the exact mapping? And Andrew's interpreter does the mapping from the input text to your S expression object. And assignment, you were supposed to do the other mapping, which is easier. Output is always easier than input parsing. But we have to understand at least with the semantics of what these textual representations are, so that we can understand them. Okay, and in terms of implementation, so in the next version of the interpreter, we've added, and I've taken actually Mac's suggestion. We've added this particular method not to the interface but to an abstract class as a protected method, and all of our types extend that abstract class, and we expect you to implement something that also that extends one of our types. If you don't use inheritance, you use delegation, things get a little problematic. But I'm expecting most of you using inheritance. So there's a toString as list helper just to implement toString as list as the way it should be implemented. Okay. So let's go and understand what the various textual representations are. Okay, and for literals, there's not much surprising stuff there. The only surprising thing there is a nil, and nil, when it is considered as a list, is just a bunch of open parentheses and one open parenthesis and one closed parenthesis without anything intervening. And when it is not considered as a list, it's just the value nil. Okay. And so we can say that toString has expression deep and toString as expression, all just go to the value, and if we are in an object-oriented language, we just assume that that value is an object, or can be converted into an object, and we just say get value dot toString, and what we see in Lisp is not different from what we would see, say, in Java. Okay. Now look at the identifier / symbol. These are the things that are analogous to and serve the same purpose as, say, Java variables. And you see something surprising there in the textual representation. Can you offer this identifier that I've shown you? Can you type that as an identifier in Java? Can you name a variable named +5 and then letters FIVE? So identifiers must start with an uppercase letter in almost every language I know. Okay, so Lisp is a little different, and you can, just because of its prefix notation, the fact that it treats operators and identifiers in a very similar way. So any string with no spaces that is not a literal can be input as an identifier. Okay, so that is, in fact, I was surprised by this myself, but apparently you can do that. Okay. And so the simple syntax and uniform prefix notation for calling things makes that possible. Okay. Questions? So you guys didn't know that variables have to begin with uppercase letters, or with letters, or was that too simple a fact? You kind of knew.
No, just the identifiers. Capital letter.
So that's a convention issue. Okay, in variable names begin with small in Java, but they can begin with capital also. But you can't begin an identifier with a number 5. Okay, you can't have an equal to sign within an identifier. Okay, so it's interesting how you can just learn by example and not know quite the rules. Okay, now when we define textual representations, there are two tensions there. As a programmer, we want to make things simple, easy to code. As users, we want things that are intuitive. And the reason why we have all these multiple text representations, I want to sort of show you the trade-off there, and show you that there's multiple reasonable answers. So from a programmer's point of view, I would like my textual representation to be this way. Okay, define it recursively. If it's composite, somehow go and say it's composite and show the two components and separate the two components, and just go recursively down. Okay. So this is a simple tree-based recursion, and you're saying that you're saying exactly what I just said earlier. Okay. So let's go and make sure that we understand how this works, because I've had so many questions about the example I gave in class in the notes. That is that right, and why your interpretation is different. Okay, so this would be 7.nil based on our thing that you have parentheses. 7 is one atom, nil is the other atom. Nil is not a this is we are not treating it as a list. We're not doing anything special for a list. So this is 7.nil within parentheses. Okay, so left component dot right component, the base case. I add another node to it. Okay, so what do I have to do? I have to take this 7.nil, make that the right-hand component of my new S expression, and sorry, the left-hand component, and the right-hand component will be nil, so I have 7.nil.nil. Okay, I add, now if I have no nil, if I have a and 6, then the answer is a.6, right? So there's nothing surprising there. If I go and add another nil to it on the right, then I just say a.6.nil. Okay, and if I build two structures here, again the left-hand component versus the right-hand component, so this just keeps going on. Okay, so that's what you would get with this implementation, and you can see that it was easy to write, but the fact that if something was a list, you don't quite see it as a list. You see that as a linked list of nested structures, and you want to see that as a flat structure of the components in the list being at the same level. Okay, so that's what you would like to have for the list. So we went to a more flexible mapping, where we said that, look, if it is a list, we'll do something special. We won't show it as a nested structure. That if it is a list from H1 to Hn, then we will just show a left paren, H1 space, H2 space, till we get to Hn. Okay. So, and then what we will do is we will look at the string and we will check whether it's a list or not. If it's a list, we'll print it as a list. If it's not a list, we'll print it as an S expression. Not as string as S expression, but not a string as S expression deep, but string as expression. So now I've got two additional methods. I've got toString as list. I've got toString, which is doing one thing or the other, and I've got toString as S expression. And what is the difference between toString as S expression and toString as S expression deep? So toString as list does not print the nil atom. toString as S expression prints the nil atom for if it's on the left hand side. I'm saying I just showed you an implementation just before this, right? toString as S expression deep, which was just a recursive method calling itself. I've got yet another method, toString as S expression here. How does that differ from toString as S expression deep? Why not just say deep to get what we want? What's intuitive?
Maybe toString as expression deep assumes the string is a tuple.
Yeah. toString as S expression deep does not do an is list. So it will work for the first level, but for the nested levels, it's, if toString as expression deep does not check for is list, so the nested list will have the nil in them. Okay. So what we will do is we have three mutually recursive methods. toString as expression is again like that toString as expression deep. It puts a left paren, right paren, a dot in between, but it calls toString on the get head and toString on get tail rather than itself on that. Okay, so I have three mutually recursive methods, and like I said, to really do things correctly, and actually the toString as list method is not recursive. I put dot dot dot. That is pretty unambiguous, but it's not precise. It's not something I can convert into an algorithm. So you really need four methods if you implement toString as list the way I've got it here, not the way I've got it in the assignment because we didn't have the help of method. So that's your flexible mapping. Okay, it's much more complicated, but it's not that much more complicated. But it's much more there's much more use of recursion. Okay, so code like this is something that I expect you guys to get in class now that you've written these methods. Okay, and you really need to sort of understand what you've done to be able to write answers like this in exams. So make sure that you really understand what you've written. And so let's go and see what happens here. Rather than 7.nil, this is where we just say 7 because this is a list. This is also a list, so we just embed the 7 within another list. This is not a list, so it doesn't have a toString as list. So the toString is the same as toString as expression deep. This is a list because it's ending in a nil in the right-hand component. So we will go and put a.6 in a list now, no nil. And this is also a list, so we'll get rid of the last nil also, and we'll put it within a list, and so on. Okay, yeah.
You said that you can't do two strings unless it's recursive.
No, I never said you can't do. I said this two-string list is not recursive. It's not. So I'm going to point that out, that this is really a So what I was trying to do was give you a specification so that you can convert it into an algorithm. And so this is a point I'm going to make it more in the next slide. Okay, so anyway, we can just keep going like this and get this. So that's the rationale. I believe the assignment is consistent with what I've got here. Okay. So I want to sort of say again something which is important, which you're bringing out. And this is from the point of view of an exam. Okay. So in an exam, I'm not going to ask you to go and write Java code. I mean, you can. It's welcome. Okay. But you can be more abstract. But you have to get the essential concepts I'm trying to get at. And in general, pseudocode and regular code are equivalent from an intellectual point of view. They have the same algorithm. Okay. So if you notice, the ones at the bottom, so all three of them were specifications I gave you. Okay, so I can give you a specification and say, give me an algorithm for it. And there may be a small distance between the specification and the algorithm, or there may be a large distance. Okay. The specification should be unambiguous. And I couldn't figure out a specification for the bottom two functions that was unambiguous and yet not equal to the implementation. Okay, and that's one of the beauties of recursion. That recursion, you can just take a specification and convert that into code, and it just works. Okay, with loops, you have to, do something more complicated. More efficient often, but more complicated. Okay. With the list, with the top one though, I put these ... dots. I think that is unambiguous. But that ... did not translate to any algorithm. So this was a harder function to implement. And you could have implemented that with this specification. You could have implemented that. All three specifications, you could have implemented them using recursion or using loops. If you use loops for the bottom two, you had to do more work. Recursive solution just followed. Okay. For the top one, you could do it recursively or iteratively using loops. And it was more challenging, and that's where you needed a helper function if you took the definition that I just provided you and used interface types. And you needed a helper function either way. So I want to make this clear that, if I ask you for a specification, I'm looking for an algorithm, and in the context of this particular class, I'm looking for the operations on S-expression nodes that I've given you, that you should be using those operations. So here I'm not, in the top one, I'm not using the head or tail operations at all on the S-expression. So that's a hint that it's a specification and not an implementation. Okay, and an implementation would use the heads and tails like you guys have done and be more complicated. Okay, so this is a specification only. Algorithm refinement required for recursive and iterative solutions that use S-expression operations. Okay, and this is both a specification and implementation of recursive algorithm. Okay, uses all necessary S-expression operations. But you'll have to translate this into an iterative solution if you really need to use loops. Okay, so in the exam, please be very conscious of this fact. Okay, because this class is going to be a little bit about writing Lisp and a lot about implementing functional languages. And when we talk of implementing functional languages, I'm talking of algorithms. Okay, so people often make a difference between theory courses and systems courses. And some people think systems courses are about learning syntax and learning APIs. Learning APIs you can do outside class too. I mean, it's just a question of knowing details. But my viewpoint always is that systems courses are just specific algorithms for practical things that you use. Like in operating systems, you learn how threads are implemented, how synchronization is implemented. And in a programming language course, you learn how the programming language is implemented. Okay. So there'll be lots of algorithms, and this is how you should address the algorithm questions. Okay. So use all relevant S-expression operations if asked for implementation algorithm. I might just ask you for specification, in which case you can be taking more liberties. Okay, so now we understand the Lisp interpreter a little bit better. So now we know that it takes as input an input S expression dot to string and creates a result S expression dot to string. And you know what I'm saying, that input S expression does not contain tuples because you can't just type in A dot B there. Okay, A dot B is not a valid input in a Lisp input. Okay, you can say const 1, 2, which becomes now, or const AB, which becomes now a function application, but you can't just type in a tuple directly. That's because you do either enter atoms or you enter function applications. And function applications are all lists with the function name being the first item and the arguments being the remaining items. Okay? Questions? Okay. So we basically do what, and like I said, the evaluate is going to be something that's defined on an S expression, and each S expression will decide how it's evaluated. And so eval is another method we've added. We've added atom, we've added is list, and we're going to add eval as a method also. And I've got an argument here called environment that you may or may not have seen, which is not relevant to your first assignment, but can you imagine what it really means? What it would mean later? Sorry? So it has to do with function calls, but what exactly? Because we know functions are coming later.
Try to pass the scope.
So function calls name formal parameters. Formal parameters are often called parameters. Formal parameters have values, which are actual parameters. Somehow there's a mapping between formal parameters and actual parameters. Okay? And that is what is going to be in our environment. Okay, so if you've implemented compilers, it's like a symbol table entry. In a compiler, an identifier is associated with an address, which will be looked up at runtime. In an interpreter, the identifier will be associated with an actual value. Okay, so we are not doing function calls right now. So our environment that you guys got was just null, and in the next assignment it will be some object, and so that's why we've kept the environment. Now, environment, you can make the environment a singleton and have it a global variable accessed by all the eval functions. We get a little bit more flexibility with passing it to the S expression because we can have multiple environments at the same time. And that will be important for eager and lazy evaluation and something called shallow and deep binding and fun args. And so, 2 points. Each S expression decides how it is evaluated. And the environment needed for programmer-defined functions. So environment is needed for programmer-defined functions. And the environment argument is given to each eval because for lazy and eager evaluation. And other constant things also. Okay, this is something that I just have kept here, which you don't immediately need, but okay. So I've added now what evaluate will actually evaluate. It will evaluate either an atom or a function application. Okay, function application is the form left paren, some f denoting a function, and a bunch of arguments. Okay, so that is what an input S expression is, and that is what we are expected to evaluate. That's what you guys are doing in your assignment. Okay, You don't quite get the full picture because you're using Andrew's interpreter. Again, you're expected to know, based on what I'm going to teach you, both how his components work and your components work. Many of your components are copies of his components, so you know how his components work. Some components you haven't looked at, which I'm going to talk about. So you're going to really try to understand, get the full picture. Okay. So we are going to have now another method in our S expressions called eval, which is both associated with an atom and an S expression. Okay. And it yields a S expression. Questions? So now we get to sort of the more conceptual part, or detailed part at least. So how would you evaluate an atom? We know an atom has a value component and we have a get value component here. So what is the general algorithm? What do you think? And this is a part that you haven't seen. This is a part that Andrew's interpreter implements. But you've used this from other expressions. So what should eval of A do? Let's say A, and we know, and A is not an identifier. Okay, we're talking of A right now as being a literal. Okay, so because and this is something I should mention explicitly, that assuming it's a literal, what should eval of A do? Get value. Just return get value here. You get 20% points for giving this answer in an exam. In fact, if you do this, your compiler will complain. So what's the signature of eval? It takes as, it's invoked on a S expression. And what is the return? S expression. A dot get value is going to return what? A Java object. Or whatever the, the native language object. So a little bit more complicated. What do you want to do now? Based on the operations we already know. It's a little louder. And do we know? So if it's an int value, we'll put it into an S expression. Okay. Use factory methods. So the signature of S expression is eval returns an S expression. So you need to wrap it into an S expression. And we now have to do something different for each kind of atom. Okay, for an integer atom, we have to call an integer expression factory. For a double atom, we have to create a double expression factory. And we have to go in, do integer factory.new instance a.get value. Okay. Assuming A is not an identifier, I should have sort of mentioned that. Okay, so is it? Okay. So need a different eval for each kind of